In 8.3, Part A, we're going to look at confidence intervals for means. Alright, so we're going to look at some confidence intervals and different ways we can calculate them using means. So what you're going to look at and try to do is to describe what happens after 1,000 samples for each setting below. And let's think about, why do some settings capture the true mean better than others? Well, first let's look at, we're trying to find z with sigma. So we know a z when we know the sigma value. So what I have for you is I've generated 1,000 confidence intervals, so teeny tiny, and the mean is actually 100, so you can see that black line is where they are. And look, they all captured really, really good using sigma. All is fine and good. We're very close to what we wanted, which was a 99% confidence level. So the capture rate of mu gets more consistently close to 99%. It is what it says it is if I use sigma, basically. But what about the reality is, if I am trying to use z and all I have is the sample standard deviation, I don't have the true population like up here. All I have is the sample. What do? Well, here I ran it with just the sample standard deviation. So you can see if in 1,000 of them, I didn't get a true capture rate of 99% confidence. What I really got was 90%. Well, the problem is there's so much error built into it because it represents only a sample, not the whole population. So we're missing the mark. And if you'll notice, there's several reds in here, meaning they did not capture the true parameter. So the capture rate's too small if I use S and I try to use a Z star value. Okay? The intervals are typically too short in that case. Well, then there's something called T. What is T? Well, look what happens if I use T. 1,000 intervals, I used T because all I have is my sample standard deviation. And in 1,000 intervals, if I wanted 99% confidence level, I actually got 99% confidence level. It's way more accurately what I want. So T intervals are longer and the capture rate is 99%, which is what I wanted. Now, why do I bring this up? Because when we switch to means using averages, we have to switch gears, and instead of using a Z value, we use a T value. So let's look at what the T distribution really is. All right, this is what the T distribution looks like. Now, honestly, the purple line is the standard normal curve. The red dotted line is the standardized T distribution when I have a sample of size 3. And the blue is the T distribution with a sample of size 10. So notice it changed. The tails are fat on the edges when my sample's really low. When my sample jumped to 10, the tails got a little skinnier and closer to the standard normal curve. So what happens is the higher your sample size, the more likely it is going to be the standard normal curve. But if you have a very, very small sample size, which is more like reality, there needs to be more area in the tails to make this work. Okay, so let's look at just shape, center, and spread of our T distribution. The shape, again, is symmetric and unimodal, but it's not quite normal. Okay, the longer tails than normal. They go on further. It approaches the standard normal distribution as the degrees of freedom increases. Now the center is still 0, just like with a normal distribution, the center is 0. In the T distribution, the center is also 0. And the spread, well, the spread is greater than the standard normal distribution. Basically, you have to go farther than 1.96 standard deviations to be 95% confident. All right, and that's all theory, but how does it work out? Well, let's look at the next slide. So the question becomes, when should you use a T star critical value than a Z star critical value when you're calculating a confidence interval for a population mean? Well, we use T star when we have to use S, the sample standard deviation, to estimate sigma, the population. Reality is, most of the time, all we have is sample data. We don't have population data. So in this course, really what you're going to see is that we use the t-distribution anytime we are encountering an average or a mean. We use the z-distribution anytime it's a proportion. So we use this little acronym, ZAPTAX. Z is for proportions, t-distribution is for averages or means. So then, okay, so if I use t instead of z, how do I find t star? And how do you calculate degrees of freedom? Well, it's in your calculator. It's based on some tables. In your calculator, in the distribution, right where you have inverse norm that we've used before, right underneath it is inverse t. When you click on that, it has two prompts. It asks you what's the area in the tail, like we've done before, and then there's something called df. That's called degrees of freedom. That only happens when you're using the t-distribution, but it's really easy to calculate. Degrees of freedom is just the sample size minus 1. It's that simple. So let me walk you through a couple. Suppose you want to construct a 90% confidence interval for the mean of a population based on a simple random sample of size 10. What critical value of t star should you use? Well, you're going to go about it the same way you would with the z star. Draw the curve. The area I want is 90% in the center. That means I have 10% split in the tails. So I have 5% here and 5% on the right side. When I convert those to decimals, I get 0.05 here, and then this one would be 0.95. In my calculator, I'm going to put an inverse t in an area of 0.05 with a degree of freedom of this 10 minus 1 gives me 9. And that gives me a t star value of positive, which would be this side of the curve, and the negative, which is this side. But they're symmetric, so it's going to be the same. So 1.833 is my critical value for that confidence interval. B, what if you want to construct a 99% confidence interval for the same size, using a sample size of 75? Well, so if 99% is in the middle this time, I have 1% I have to split among the tails. So there's 0.5% on the left, 0.5% on the right. Convert those to decimals, I get 0.005 and 0.995. Inverse t, I put in my area. My degrees of freedom is 74 because my sample size was 75. And that generates a t star value of positive and negative 2.644. What are the three conditions for constructing a confidence interval for a population mean? These should begin to look familiar. Number 1, has to be random sampling or a random experiment. Has to pass the 10% condition for independence. And then thirdly, we have to have a normal sampling distribution or a large enough sample, and that's using the central limit theorem we've discussed in the previous chapter. So then what happens if these aren't met? What if they fail one of these? Well, if it's not random, that means that whatever conclusion you make, you can't make an inference about the whole population. You can only make it for that sample. What if it's not independent? Well, that means that you really can't calculate the standard error of your x bars. That's going to be a problem as we proceed. What if it's not large or normal in shape in your sampling distribution? Well, what's going to happen is you can still calculate an interval, but the capture rate is not going to be what it's supposed to be. Like, if you want to be 99% confident, what would happen is you'd probably only be 90% confident. You could still get an interval, it's just not going to be as good. So some formulas for you. What's the formula for the standard error of the sample mean? And is this on the formula sheet? Well, yes it is. Standard error of the sample mean looks like this. It's the sample standard deviation divided by the square root of my sample size. Okay? This is what we're going to use in our margin of error when we do confidence intervals. Now, what's the formula for the confidence interval? Well, it looks like this. It starts with the sample mean of x bar. We add and subtract the product of this back here, a t star times my standard error of x bar. Now, it's not exactly on the formula chart like this. Remember, on the formula chart it looks like this. It's very, very generic. You just plug in the right values in the right places. In the next video, we'll actually calculate some confidence intervals with means.